In the last class we were looking at the dual of this particular minimization problem. When we began our discussion on the dual, we took a maximization problem with all less than or equal to constraints and all variables greater than or equal to 0, and the dual was a minimization problem with all greater than equal to constraints and all variables greater than or equal to 0. Now we then pose the next question of, if I have a problem with different types of constraints and different types of variables, how does the dual look like? So to explain that, we looked at this problem, which is a minimization problem with 3 different types of constraints that we have here: an equation, a less than or equal to, and a greater than or equal to. And we also had 3 types of variables: a greater than or equal to variable, an unrestricted variable, and a less than or equal to variable. Now we said that we have to bring this to a form which is comfortable to us, which is the form of maximization with all constraints less than or equal to and all variables greater than or equal to. So we first redefine these variables such that they become greater than or equal to type. So x2 was redefined as x4 minus x5, x3 was redefined as minus x6, and we had a problem which was written like this. Now you realize that this phi x2 has become phi x4 minus phi x5 and so on. This 8x3 has become minus 8x6. Now x6 is greater than or equal to 0, x4, x5 are also greater than or equal to 0. Now we have brought it to the form where all the variables are of the required type, which is greater than or equal to type. Now we have to bring it to the form where all the constraints are of the required type. So what we did was, we retained this less than or equal to constraint, we multiplied here with a minus 1, we multiplied this with a minus 1, entire constraint with a minus 1, so that we get a less than or equal to, the 9 would become minus 9. We multiplied this also with minus 1, so that we get less than or equal to. The equation was written as 2 constraints, the same left hand side greater than or equal to 12, the same left hand side less than or equal to 12. We retained the less than or equal to, we multiplied the greater than or equal to by minus 1. So when we did all that, we got this form. Now we wrote the primal in a form where all the variables are less than or equal to. Now all the variables are less than or equal to, all the variables are greater than or equal to, and all the constraints are less than or equal to. Now we know to write the dual to a primal of this form, and then we wrote the dual to the primal of this form. But meanwhile, because we brought all the variables to greater than or equal to, we added one more variable, the unrestricted resulted in an extra variable. We brought all the constraints to less than equal to, so the equation resulted in an additional constraint. There was one greater than equal to, one less than equal to. So the original, and we of course multiplied the objective function with minus 1 to make it a maximization. So the original problem has 3 variables and 4 constraints. Now the modified problem has 4 variables and 5 constraints. So now we write the dual of this problem. I have shown the same problem here. Now we can write the dual. We will now introduce dual variables y1, y2, y3, y4 and y5. There will be 5 dual variables. There will be 4 dual constraints corresponding to the 4 primal variables. These right hand side values will become objective function values. These objective function values will become right hand side values. So the dual will look like this. The dual is now a minimization problem with 5 variables y1, y2, y3, y4 and y5, with the right hand side values of this, with these right hand side values becoming the values of the objective function. Now these objective function values became the right hand side values. The transpose of the matrix repeated. For example, the first constraint would be minus 4x1 be minus 4x1 plus minus 4y1 plus 4y2 minus 7y3 plus 8y4 minus 3y5 greater than or equal to minus 8. So, we can write the dual this way. Now, having written the dual this way, we realize that the dual now has 5 variables and 4 constraints. The original problem had only 3 variables and 4 constraints. Therefore, the dual should have 4 variables and 3 constraints. Plus, the original problem's objective function should be the right hand side of the dual and so on. So, we now have to modify this and bring it to a form which is consistent with the earlier table that we had seen. So, first thing that we observe from this is, if we look at these two constraints, you realize that we can multiply the first constraint with a minus 1, we will get 2y1 minus 2y2 plus 5y3 minus 5y4 plus 7y5 is less than or equal to 5. And the same thing is now greater than or equal to 5 as another constraint. Therefore, we can merge these two constraints to get an equation. So, this is the dual that we had written. So, this dual has 5 variables and 4 constraints. So, the first observation that we have is, we have this, the first constraint of the dual has a minus 8 in the right hand side. So, we try to bring it to a plus 8 by multiplying this constraint with a minus 1, so that the right hand side values is positive. Second observation that we have is, these two constraints are similar. So, if we multiply this first constraint with a minus 1, we would get 2y1 minus 2y2 plus 5y3 minus 5y4 plus 7y5 less than or equal to 5. The next thing has the same left hand side greater than or equal to 5. We can merge these two and make them into an equation. So, we now do these two things. So, we have now converted the first constraint this way by multiplying it with a minus 1. So, 4y1 minus 4y2 plus 7y3 minus 8y4 plus 3y5 is less than or equal to 8. And as I mentioned, this constraint is multiplied, with minus 1 made into a less than or equal to, and then merged with the next one to give 2y1 minus 2y2 plus 5y3 minus 5y4 plus 7y5 equal to 5. This constraint is retained as it is because the right hand side value is plus 4. So, we have plus 4, it is retained. So, now what we have achieved is, we have done one thing where the right hand side values here are 8, 5 and 4 with a plus sign, and these are exactly the objective function values of the given original problem. Then when we take a look at this, we realize now that if we look at this variable y4, we realize that all the 3 coefficients are negative for the variable y4, and y4 is greater than or equal to 0. So, we can now replace y4 by another variable, call it y6, and then we can make this variable less than or equal to 0, so that the objective function, the constraint coefficients are all positive. So, we do that next. Now, you observe that minus 8y4 has become plus 8y6, minus 5 y4 has become plus 5y6 and so on. y6 has become less than or equal to 0, y6 has become less than or equal to 0, plus 10y4 has become minus 10y6. The other thing that we observe here is, we see 4y1 minus 4y2, 2y1 minus 2y2, 8y1 minus 8y2. Now y1 minus y2 can be bunched together and can be made as an unrestricted variable. So we introduce a y7 which is an unrestricted variable, and that becomes, now we have minimize minus 12y7 because y1 minus y2 is the unrestricted variable, minus 12y7 minus 9y3 minus 10y6 minus 7y5, and more importantly we have all the constraint coefficients now are the positive numbers. Now the constraint matrix here of the dual is exactly the transpose of that of the given original problem. The right hand side values are the objective function values, but in the process y7 has been introduced as an unrestricted variable. Now from here we introduced an unrestricted variable, so the number of variables reduced by 1. We merge two constraints to an equation where the number of constraints reduced by 1. Now the dual has 4 variables and 3 constraints. The original primal had 3 variables and 4 constraints. So the only thing that remains is, we have a minimization with all negative coefficients, multiply with minus 1 to get a maximization, and when we do that we get this. So we have maximized 12y7 plus 9y3 plus 10y6 plus 7y5 and so on. Next thing we do is, we simply rename the variables. To be consistent, we call them as y1, y2, y3, y4. The variables are renamed. So y7 becomes y1, y3 becomes y2, y6 becomes y3, y5 becomes y4, and it is rewritten this way. So the dual is now a maximization problem with 4 variables and 3 constraints. Now we go back and try to compare it with the original primal, the problem with which we started, and the original primal is like this. Now we can do a mapping. What we had seen earlier, we can now do that mapping. We now realize that the original primal is a minimization problem, its dual is a maximization problem. The original primal has 4 constraints, the dual has 4 variables y1 to y4. The original primal had 3 variables, the dual has 3 constraints. The objective function values are 8, 5 and 4, the right hand side values are 8, 5 and 4. The right hand side values of the primal are 12, 9, 10 and 7, objective function is 12, 9, 10 and 7. The given matrix is here, the transpose is here. 4 to 8 is the row, 4 to 8 is the column. So we have the same thing. The only difference is, we now have to see what happens to the sign of these. How are these sign of these inequalities? How are these signs related to the primal, and how are these signs related to the primal? That is the only thing that remains that we have to see. So what we can do is, if we are given any primal, we can simply write, the primal is minimization, you can write a maximization, you can introduce the variables, you can do everything, except that these 3 things have to be filled and these 4 things have to be filled. So we need to find out what is the inequality or equation of the particular constraint and what is the sign of the particular variable. That is something which we need to do. Now to do that, let us revisit this again. This table we have already seen. If the primal is a maximization, the dual is a minimization, and vice versa. The number of variables of the primal is equal to number of constraints of the dual. Number of constraints of the primal is equal to number of variables of the dual. right hand side of the primal becomes objective function of the dual, objective function of the primal becomes right hand side of the dual, the A matrix, the constraint coefficient matrix becomes the transpose. This we have already seen. Now this is a new thing that we are now going to see. Now to see this, we go back to the previous, where the primal is a minimization problem, the dual is a maximization problem. Now in the primal, the first constraint is an equation. Now remember, there are 4 constraints here, therefore there are 4 variables here. There are 3 variables here, there are 3 constraints here. So there is a relationship between constraint and variable, and a relationship between variable and constraint. So we observe that the first constraint is an equation, first constraint is an equation, the first variable becomes unrestricted inside. The second variable is unrestricted in sign, the second constraint becomes an equation. So there is a relationship between this equation and the unrestricted variable. So if the ith constraint is an equation in the primal, then the ith variable will be unrestricted in the dual. If the jth variable is unrestricted in the primal, the jth constraint will be an equation in the dual. This is also understandable because if we, for example, if we looked at this equation, in the conversion process we wrote this equation as 2 constraints. Now these 2 constraints resulted in 2 variables in the dual, which were subsequently merged into an unrestricted variable. So an equation constraint results in an unrestricted variable. The unrestricted variable got expanded to 2 variables, and then it became 2 constraints, and these 2 constraints were merged into an equation. So the unrestricted variable corresponds to an equation constraint. So that relationship we can comfortably find out. The other thing is, in the minimization, the first variable is greater than or equal to 0. In the maximization dual, the first constraint is less than or equal to. In the minimization, the third variable is less than or equal to. In the maximization, the third constraint is greater than or equal to. In the minimization primal, the second constraint is greater than or equal to. Here the second variable is greater than or equal to. So that relationship we need to understand. Now that relationship we are trying to capture here. So if now whatever problem is given as a primal problem, in our example the minimization was the primal problem. So this part is now becoming the primal for our discussion. So this part is the primal for our discussion. This will be dual for our discussion, because our original problem was, the given problem is a minimization problem. So if the primal is a minimization problem, if I have a greater than or equal to variable, then the corresponding dual constraint will be a less than or equal to constraint. If I have a less than or equal to variable in a minimization primal, the corresponding constraint will be a greater than or equal to. Similarly, if I have a greater than or equal to constraint in a minimization primal, then the corresponding variable in the dual will be greater than or equal to. If I have less than or equal to constraint in the minimization primal, the corresponding variable will be less than or equal to. Alternately, if the primal happens to be maximization, and if I have a less than equal to constraint, then the corresponding variable in the dual will be a greater than or equal to variable. Now the way we explain is, if the second constraint is a less than or equal to constraint in a maximization primal, then the second variable will be a greater than or equal to variable in the minimization dual. So if I have a greater than or equal to constraint in the maximization primal, the corresponding variable will be less than or equal to time. Similarly, if I have a greater than or equal to variable in a maximization primal, the constraint will be greater than or equal to in the minimization dual, and if I have a less than or equal to variable in the maximization primal, I will have a less than or equal to constraint in the minimization dual. Now, these 4 things we need to remember when we write the primal and the dual. So, one way is to remember them, the other way is also to say that in any linear programming problem, we have a greater than or equal to variable is a good variable with which we can start the simplex algorithm. For a minimization problem, usually we find greater than or equal to constraints as the correct type of constraint, and for a maximization problem we find less than equal to constraint as the correct type of constraint. So, we can think the correct variable will match with the correct type of variable and the correct constraint will match with the correct type of constraint. For example, maximization problem less than equal to is a correct type of constraint. So, the greater than equal to variable is the correct type of variable that will come. For a maximization, greater than or equal to is not a very correct type of constraint. Usually you have less than equal to constraints there. So, minimization will have the opposite, it will have a less than or equal to variable. Similarly, greater than equal to variable is the correct type of variable. So, greater than equal to constraint for a minimization is the right kind of constraint. So, the correct kind of variable will map to a correct type of constraint, and the not so desirable type of variable will map to a not so desirable type of constraint. So, this way, using both these tables, we will be able to write the primal the dual for a given primal. So, we now have to answer the next question. Having understood what is the dual and having learnt how to write the dual for a given primal, we have to ask the next question: why is the dual important? After all, these two problems, one comes from the other, and how are they otherwise related? So, we now look at what is called primal dual relationships, or understanding the dual further through some results and theorems, which we will see in the next class.